We'll talk about Galois extensions today. So first the definition. So let K be an algebraic extension. Let K over F be an algebraic extension. Okay. We say that this is Galois. We say this is a Galois extension. If it has two properties. Number one, K over F is a normal extension, and number two, if it is a separable extension. So we talked about both these adjectives already. When is an extension called normal, when is an extension called separable, and if an extension has both these properties, then it is called a Galois extension. Okay, it's a normal separable extension. And notice here that we don't really require that K over F should be a finite extension and so on. All we demand is that to begin with, that it should be an algebraic extension, could be an infinite or a finite extension. Okay, but of course eventually we will restrict ourselves to a more in-depth analysis of the finite Galois extensions. But the definition is completely general. And so quickly let's see the examples. So if I take my base field F to be the field Q, and if I take any polynomial fx in Qx, okay, and if I define K to be the splitting field of this polynomial. So what I can do is to take K, define K to be the splitting field of this polynomial f, then K over F is automatically Galois. K over F is a Galois extension. Okay, why is this? We just need to check the two adjectives, the two properties it's supposed to have. Because it is a splitting field of a polynomial, it is normal. So recall, this is one of the definitions or characterizations of a normal extension. So this tells you that K is normal. And K is separable comes for free, because recall Q is a characteristic zero field, and we talked about this when we talked about separable extensions and so on. Any algebraic extension over a characteristic zero field is automatically separable. Okay, so K is separable since characteristic of Q is 0. And recall, we also have a version of this for characteristic P. In that case, we require the field to be perfect. Okay, so so Galois extension. Okay, so now let's look at a second example, which is for finite fields. If I take F to be Fp, then recall, in this case it has finite characteristic, but recall that F is perfect. Okay, and that meant that the Frobenius map is an automorphism of the field. And in this case, again, we have seen the following, that you will get separability for free. If K is algebraic extension of F, then separability is automatic, because the definition of separability is that every reducible polynomial, so you take any element of the extension field, its minimal irreducible polynomial over the base field must be a separable polynomial. Okay, must have distinct roots. And if F is perfect, then we have seen that any reducible polynomial is automatically separable. Okay, so this just comes from our lecture on separable polynomials and so on. So in this case again, so let me take my field K to be the field Fp to the n. Let's say for any n greater than or equal to 1, I'll take K also to be the finite field with p to the n elements now. Then K over F is a Galois extension. Okay, why is it a Galois extension? Well, as I just said, separability. K is separable because F is a perfect field. Okay, and K is of course in this case a finite extension of F, so it's definitely an algebraic extension. So this is the automatic property. The normality is what we need to check. So can we realize K as the splitting field of some polynomial? But recall that's exactly how the finite fields were constructed. Recall from the lecture on finite fields, recall K, which is f p to the n, is nothing but the splitting field over, so I mean the base field here is fp of the polynomial x to the p to the n minus x. Okay, in fact that's exactly how finite fields were constructed, as splitting fields of this particular polynomial. So it's therefore normal, so which implies this is a normal extension. What's the normal extension? K over f. And so we have both properties. It's so I should have said here again, it's a separable extension. Okay, so it has both properties, so it is Galois. Okay, now we could talk about lots more examples, but for the moment let's first look at some equivalent characterizations of Galois extensions. For that I need a definition. So let me say if K is a field, so let K be a field, and look at the set aut K, which is the set of all field automorphisms of K. Okay, so when I say aut of K, I always mean K is a field, so I'm thinking of this as a set of all maps from K to K, which are field automorphisms. So field automorphisms of K. Okay, and so I take K a field and I take a subgroup. So let me call this subgroup as gamma. So let gamma be a subgroup of the group of automorphisms. Okay, the automorphisms form a group as always. So if I take gamma a subgroup, then the definition is the following. So let K be field, gamma be a subgroup, then we write K superscript gamma, K gamma, to be the set of all elements of K which are fixed by every element of gamma. Okay, so sigma of A should be A, and this should be true for every sigma and gamma. Okay, so this K gamma then is, so let's check the following simple property. K gamma is in fact a field. Well, it's actually a subfield of K. This is a subfield of the ambient field K. Okay, so let's check this. So what is it that we need to check? We need to check the properties of a subfield. What all do we need? Well, if you have two elements A and B in the subset, when is a subset a subfield? If you take two elements A and B, then you have to check that A plus B is in the subset. The algebraic, the additive inverse minus A is in the subset, the product is there, and the multiplicative inverse is there. This is for A not 0. So it's closed under taking under addition, multiplication, and additive inverses and multiplicative inverses. Now I'll just check a couple of these properties. They're all very easy. So how do you check this, for instance? So to check that A plus B is in K gamma, you need to check the following: whether every element of gamma fixes the element A plus B. So you apply sigma to A plus B. Sigma is an element of gamma, so need to check the following: for every sigma in gamma, I need to check that sigma of A plus B equals A plus B. But sigma of A plus B is just sigma A plus sigma B, because sigma is an automorphism of the field and both A and B come from K gamma, therefore they are fixed by sigma. Okay, so that shows that A plus B is also fixed by sigma. Similarly, let's check the last one. If I had to check that A inverse belongs to K gamma, I need to apply sigma to A inverse. But again, sigma is an automorphism, therefore we have the following property: sigma A inverse is sigma A the whole inverse. But sigma A is just A because A belongs to K gamma. Okay, so and so on. You can just check the other two properties similarly. So this is a subfield, and this is usually what's called the fixed field of gamma. Okay, so this is called the fixed field of this subgroup gamma, or sometimes called the field of gamma invariants, the subfield of gamma invariants. Okay, so you'll see all these terms used. Now observe we didn't really use the fact that gamma is a subgroup for any of this. In fact, if you just take any subset, this will still work the same way. It will turn out to be a subfield, but we will almost always only be interested in the case when gamma is a subgroup. That's what's going to occur again and again when we study Galois theory. Okay, now let me define another notion. So I just talked about the group of automorphisms. Now if K is an extension of F, so K over F, let K be an extension of F, then we define let aut K over F denote the set of all field automorphisms of K which have the following property, that when you restrict them to F, it just gives you the identity map on F. Okay, so this in fact came up earlier when we talked about normal extensions and so on. So these are exactly the maps from K to K, the sigmas, which when you restrict to the base field is just the identity on the base field. So they fix the base field. Okay, so this is called aut K over F, sometimes called the group of F automorphisms of K. And observe that this is a subgroup of aut K. Aut K is all field automorphisms, even ones which don't fix F pointwise. But when we think about extension fields having K and F, then the natural notion really is that of aut K over F, okay, automorphisms which fix the base field.